So, I'm Enoki from the University of Electrical Communication in Tokyo. My collaborators, Professor Agung, Professor Budi, and Dr. Indri, are also including as co-authors. So I'll talk about correlation of pressure drop in the sintered fibrous porous tube with permeability and friction coefficient. First, the motivation and the introduction of this study. My study is improving the performance of the heat exchanger. The heat exchanger used as a very important element devices in various machines. But the main problem in efficiency of heat exchanger since the heat transfer coefficient on the air side is poor. So it is necessary to increase the heat transfer area. As a result, the heat exchanger must be increased in size. Therefore, we have developed a new sintered aluminum heat transfer tubes with a fiber made of the same aluminum. This figure shows the experiments with the inner diameter. This figure, inner diameter 18 millimeter, and the porosity is 80% with dry air. The upper triangle indicate the temperature at the inlet, almost 200 degrees Celsius. And the lower triangle indicates the temperature at the outlet. As shown in this figure, the double tube structure is used to cool the outside cold water at 1 degree Celsius. The total length of the tubes is 450 millimeter, but the filling length of the porous fiber is very small, 25, 50, 75 millimeter, which corresponding to the length of the thumb. That is to say, we have success in reducing the length of the heat transfer tubes 100. Because conventional diameter tubes require the length 3,000 or more to cool down from 200 degrees Celsius to 30 degrees Celsius. So 450 millimeter heat transfer tubes comes out at normal tubes is 105 degrees Celsius, but only 25 millimeter filling tubes come out 30 degree, and 50 millimeter filling tubes comes out 5 degrees Celsius, almost cooling water temperature. In other words, we have succeeded in a breakthrough in heat transfer, where the heat transfer coefficient of air side is greater than that of water forced convection. This topic was presented as a keynote speaker last year. The goal of this study is to develop an equation for heat transfer coefficient and pressure drop for the design of a sintered fiber heat exchangers. We have already proposed a correlation that can accurately predict the heat transfer coefficient regardless of the pipe diameter and filling length. So today's topic is about understanding the mechanism of pressure drop and the construction and equation. The experimental conditions are as shown in this table, using dry air with 0% relative humidity. In particular, the four main parameters, circular in red, are very important. Inner diameter, porous filling length, porosity, fiber diameter. And we conducted experiment to construct formulas that take these effects into account. Now let's start with the basic to make correlation. There is a Darcy laws used in civil engineering that describe the relation between the velocity of water flowing through the soil and the pressure drop. It can be applied very slow velocity, and the Reynolds number is about 1 to 10. In this case, permeability copper is very important, but it is not possible to measure it directly, so it is necessary to perform experiments. In addition, there is an extended Darcy law, which is applicable not only slow velocity conditions experiment in terms of the viscous term, but also to cases where inertia term is needed. Here, C in the inertia term cannot be measured directly as well as copper, but must be clarified by experiment. So how do we find copper and C? This graph shows the relationship between the pressure drop gradient and the air velocity. The orange plot is the experimental value, and the solid line is the fitting function. Thus, the pressure drop can be neatly organized as a quadratic function of velocity. If we focus on the constant of the velocity term, we can find the first order viscosity term is about 2000. And the second order inertial terms about 900. Furthermore, since the viscosity and density physical property, they can be easily calculated so that kappa and C can be found and the extended Darcy law can be used. This method can be used to organize the pressure drop of porous material regardless of the fluid. Let's compare with other researchers on this extended Darcy-Ross. The comparison here, we compare the data obtained water with from PEC. It shows very good agreement with our air data. However, there is some variability, and we have explored why. Consider the new physical mechanism. When passing through a porous body, the fluid velocity should change with the porosity eta. In previous study, there is no correlation that considered this mechanism, including PEC. Since it is an impactful, the law of conservation of mass holds. In other words, if the channel is narrowing and the conservation of mass laws holds, the velocity should be increased in the porous. Therefore, it was decided to use the representative velocity of the fluid that takes into account the flow velocity variation by porosity. The results are shown in these figures. Independent of the four important parameters, we found that experimental values have very good accuracy. By incorporating the velocity variation of the porosity, the pressure drop estimate was increased by about twice as much as before. This is the conclusion. That's all. Thank you.